For this presentation, we will talk to you about how me and Tjark collaborated to achieve agent-based simulations of urban mobility futures. And without further ado, I would like to introduce first the fact that this is done in the scope of a collaboration between our two PhD topics, mine focusing on mobility simulations in the scope of my thesis regarding mobility on demand, and Tjark's work focusing on urban mobility futures and the scenario-based assessment of urban mobility. The first discipline is rather quantitative, relying on models and simulation to achieve results, while the second one is more qualitative in its approaches. And the idea behind this work was to bring a bridge between the two and achieve better estimations and better assessments of future mobility, futures of mobility. And so I will introduce the two topics separately. The first is mine regarding agent-based simulations. We have in the literature different framework and different simulation models and tools that are more or less useful depending on the objectives. We rely on a platform called MatSim, which is an activity-based, agent-based simulator that allows to study the dynamic interactions between the agents of mobility, travelers, vehicles, all located in the road network. And the advantage between these approaches is to allow the estimations on of impact on people's choices and how different mobility performances affect their choices and their model choices more specifically. To introduce a little bit the topic, we have what we call agents, which are travelers that can move through the network to achieve their activities. And the network is characterized by a set of streets with speeds and capacities, which allows to reproduce congestion. We simulate periods of 24 hours. These are considered to be average weekdays. And the idea behind all this process is that it is agent-based, meaning that every agent tries to optimize its own performance, relying on an estimation of its total utility that can depend on time spent in traveling and cost of travel, etc. Regarding the data feeding such simulations, we rely on different types of data which are fully open and accessible in the French context, going from census data to transport surveys to companies registry, etc. And this allows us to generate what we call synthetic population, which are lists of agents with daily plans and activities that are considered to represent the real life population and the real life mobility. And we are able to do that on an individual level, but also on a household level to have household level interactions, like one vehicle being present in the household, etc. Regarding the details on how each agent optimizes its daily schedule, we focus more specifically on what modes are used for what trips. In this graphic, you can see boxes that we call activities, which are chained. So this represents the daily plan of the agents that it wants to perform during the day. For example, we have home, then school, then home, then leisure, then home. And the idea is to choose the best chain of modes to take for trips between each two consecutive activities. And the idea is to evaluate all possible combinations and choose and have the tendency to choose the one that produces the best utility. And this utility is estimated in terms of travel time, travel cost, and specific modal preferences that are estimated from household travel surveys in our case. Regarding the work performed by Tjark and the urban mobility future, this is a snippet of the model of the urban mobility system model that he developed. We have 3 layers going from infrastructure to services to people. And the novel idea here is that people themselves are considered to be one of the layers that needs to be specifically addressed in mobility studies. And this is what makes this approach more human-centered, I would say. And then for the modeling of people, not only general characteristics are considered, but individual level characteristics should be considered when studying mobility systems, ranging from socioeconomic profile and types of activities to preferences like value of time and access to information. Resources ought to be considered too, such as available vehicles in household and the absence or presence of a driving license for a certain individual, etc. And this leads to the definition of the notion of personas, which is an in the middle level between the whole population and the individual. The idea here is that a persona is a description that applies to a certain type of people, and the persona profile here is to illustrate the characteristics of these people and how they differ between each other. And here, this is one graphic that is very beloved by Tjark, which shows the idea that as we move forward into the future, as the number of possibilities and potential futures increases, in most studies, especially coming from my field on agent-based simulation, only one future is considered in the studies, but this increases the dependency on assumption regarding that future. And in our approach, we rather consider multiple futures that tend to reflect a different evolution of tendencies and different assumptions on the evolution both of mobility systems and the tendencies behind the socioeconomic trends. And so the research question here was really how to develop an integrated approach for the simulation of urban mobility scenarios that can provide quantitative analysis, but can also rely on strong qualitative inputs regarding possible mobility futures. So first is the design challenge of these mobility futures solution. As Flor introduced earlier, we adopt a localized approach where we focus on one territory and tackle the mobility of that territory. Here we focus in the Anthropolis share more specifically on the area of Paris-Saclay. In the map, it's shown in yellow. It's located in Ile-de-France, as many of you know, and it is the context of major evolutions, both on the mobility offer with new lines coming like the Metro 18, and also in the locations of activities and future housings that are developed in the area. So the first challenge here is to be able to understand and measure the impacts of these new mobility solutions under the context of estimated future mobility demands. And one increasingly trending solution is the exploration of on-demand mobility systems, relying on autonomous vehicles to provide on-demand trips. Such systems are highly investigated in the quantitative literature with design decisions like fleet size and types of operational algorithms behind that, etc. And here in the area of Paris-Saclay, where we have a mix between highly dense areas and lowly dense populated areas, such services can offer increased interest to be able to connect the areas further. And also, there is this promise of more flexibility and less price due to the non-dependency on drivers, etc. And another challenge here would be to be able to simulate the impact that these systems would have, not only in one estimated futures like most of the quantitative researchers, but more on more possible futures and have a more robust analysis. And so this is one example of a research question that is often tackled in many papers in the literature, which is what is the necessary fleet size to achieve a certain service quality. So here in this graphic, for example, you have the rejection rate, which reflects the number of requests we are able to satisfy according to the fleet size. But again, this is mostly done given one assumption of demand, of predicted demand, that may be more or less dependent on a few hypotheses. And again, the goal in this presentation would be to be able to test the design of a system on various futures. And this is mostly because between the moment an idea of a project or a mobility solution is first discussed and its deployment in the real world context, we can see a decade or two in between, during which many changes can happen, both on the mobility offer context, which can be more or less predicted given the availability or not of data, but also changes on the demand and the habits of people and the distribution of where they live versus where they perform their activities, that can render the assumptions taken during the design completely depreciated. And so this is a real challenge that needs to be addressed. And again, this raises the need for having different set of assumptions for the future. And without further ado, I would like to pass the hand to Tjark for the following of the presentation. Thank you.
Hello, everyone. Thank you for joining us today. And thank you, Tarek, for the introduction. Sorry for not being there with you today, but I will do my best to present from this side how we have been addressing the issue of scenario and simulation. And for that, I will jump directly into the second part of the presentation, where I will present the methodology which we have created. To start with, what Tarek already introduced is on the one side related to simulation. So this is what Tarek is working on. It is, for example, the preparation of the synthetic populations, the integration of new mobility services, the simulation and the use case, which can be, for example, the impact assessment of a new service. On the other side, I'm working on this creation of scenarios with narratives, with personas, the localization of scenarios, and also use cases such as, for example, the impact assessment of new services. What we are trying to do is look at them together and integrate, in particular, future scenarios into the existing simulation workflow. For that, this is one of the key figures. We are trying to combine all the different elements which we have earlier introduced. So on the one side, we have scenarios. Here you see 4 different scenarios, which are aligned to the archetypical scenarios developed by Mishkolsky et al. 2021. You have Crumpy Old Transport at an easy pace, minus yours, and tech eager. At the basis of these archetypical scenarios, we localize them in the context of Paris or Paris-Saclay with the 3 different layers of the urban mobility system. The first one being people, the second infrastructures, the third mobility services. This means integrating trends, but also uncertainties. For some of the uncertainties, we just gave some examples here on the right. So an uncertainty can be, for example, the car ownership rate, the proximity, the average proximity between home and work or home and school, or the household size, each of them with an impact on the mobility behaviors. Then here we just want to focus on one layer, and this is a layer of people or users. For that, we have created 16 personas from census data and mobility survey data. And we do that in order to represent heterogeneous urbanite profiles. So we cannot work with each individual, but we are trying to see how many larger clusters, categories are there, which we can integrate in our methods. Then in the next step, we are reweighting them to attain target values for each of the uncertainties. So here you see the today's situation, you see a number of personas with the number of times they exist in the current population. And that results in a value, for example, of a car ownership of 0.88. Then for each of the scenarios, we have a predefined target rate, such as 0.8 or 0.87, depending on the archetypical scenario it represents. and we are reweighting them to match the uncertainties across multiple values through iterative proportional fitting. So this is the, let's say, the more methodological part behind. The outcome of this step is that we have the personas of today and of tomorrow, and we have the synthetic population of today and a set of synthetic populations of tomorrow. Tomorrow in this case always means 2030 as our focus in this study. Now, if we look back at the different parts, so there remains the preparation for the simulations, there remains the scenario creation and localization, but then there's integration where the synthetic populations feed into the existing simulation pipeline, resulting in the simulation, and finally the use case. And this is what I would like to talk about now in the last part. So we will not be able to show all our results, and we're happy to share more about our work, but here we'll just pick out some of the things which resulted from this work. And our use case was comparing the impacts of different potential future solutions across different dimensions. Here we are just taking the SDG 11.2, which asks for safe, affordable, accessible, and sustainable transport for all. So a bit simplified, we look at environmental, social, economic things, emissions, accessibility, and mobility cost. Here, we're going to focus on emissions because of the interest of time, and emissions in this case means CO2 equivalent. To do so, we can look at the outcomes of the simulations at different levels. Here you see the CO2 equivalent emissions today on the left and in 2030. 2030 once without SAEV, without shared autonomous electric vehicles, and once with. And the blue part is all of Ile-de-France except CPS, and the yellow part is CPS. So you see there's a significant decrease, first of all, between today and 2030. And then there's a 7% decrease roughly in CPS and a 0.3 decrease in the rest. And we can interpret this in three different ways. First, the improvement, despite a rise of cars and rise of population, the improvement of energy efficiency of vehicles, or emission, say the reduction of the emissions of vehicles, we have an overall significant decrease. Then we still have a decrease resulting from the introduction of the service, mostly within CPS, where the service is introduced, but also with some spillover effects, for example, due to people who are coming from elsewhere, but then now can use public transportation because they have a way to get from the transportation stop to their work. But this didn't introduce the scenarios yet. So in the next step, we can zoom a bit in. Now we're only looking at CPS. Again, we see the overall emissions, which are simulated for today by car, by passengers, so people from the same household who are driving together with other people, and by public transportation. And then here on the right side, you see for 2030 the four different scenarios, which I introduced earlier: good old transport, minus yours at an easy pace, and tech eager, each time in their base version and in their version with SAEV. And what you can see here can be summarized in three different parts. First, as mentioned before, the vehicle improvement is the most significant decrease of emissions. Second, the variation between the different scenarios, meaning more people are using public transportation, more people are using or living in different places. So all the behavioral changes primarily are having the highest second impact. As you see, for example, the tech eager has the highest emissions, at an easy pace has the lowest emission. And thirdly, the SAEV are leading to a decrease across all of the scenarios. But this change of or the reduction is very dependent on the scenario. So if in the tech eager on a minus euro scenario, there's a much higher dependence on vehicles, individual vehicles, thus SAEV has a much higher potential user share, thus a higher impact. While at an easy pace, the impact is much lower. Then we can also look at it at the individual level. So I earlier introduced the idea of personas, 16 in the case of Ile-de-France. And you see here one on the left with a bit of a description. But the point here is that we can look again at CO2 emissions, but also the other indicators such as the distance, the time, the expenses. And the dotted line you see for each of them is the average of all people in 2030. And then you see how Celine, in this case, relates or compares today with her daily CO2 equivalent emissions. And you see that she is producing less than others. Then in 2030, she is producing even less than others. And there's no visible impact from the emissions because probably she is not changing the mode. However, there are changes in other categories. That might be that she is saving time or more time is added due to different types of congestion or other things. So this is just to show a little bit how we can look at the different personas, how we can utilize them to try to understand who's emitting more, who's emitting less, but also who's impacted in which way by interventions which we are studying. Coming to the conclusions, the general conclusions and some recommendations. So from this application case, we can take 4 main takeaways. First, the highest emission reduction in our case has always resulted from vehicle efficiency, meaning smaller cars with with newer vehicles and so on. Of course, that depends on the life cycle emissions and so on, but generally the vehicle efficiency was the biggest impact on emissions. The next highest impact resulted from the different scenarios. That means different behaviors. That means different type of people who are living and moving around in different areas. And only then the technological solution, the SAEV, showed a significant impact. And then finally, as just talked about before, there are significant difference between the personas, and this could be used for a lot of different things. It could permit targeted policies, targeted incentive strategies, and so on and so on. So this is the application case on the methodological side, while many limitations remain, which we are happy to discuss further. We proposed a method which permits up to a certain degree to model future mobility solutions across different scenarios, thus integrating future uncertainties and estimate the impacts across different environmental, social, and economic dimensions. Further, we identified the potential to compare not just no solution to one solution, but also look at several solutions and their interactions between each other. And for this, I will just very briefly introduce the second case study, which we have been working on, which is in Cairo. And the idea is more or less we are looking again at the metropolitan scale. So at Greater Cairo, you have about 22 million people living in this area, which is here outlined with the dark bold line. It results from a collaboration with the American University in Cairo and Transport for Cairo. And through a co-creative process, again, we created 4 different scenarios. There are 2 critical uncertainties here, which we used by using a 2x2 matrix, where we varied between sprawl and densification and a rising car ownership or a stable car ownership. And you see a representative visualization here for each of them. But the idea is the same. We take context, we localize scenarios. In this case, we are looking at 4 different solutions. Before we looked at one, being the SAV. Now we look at bus rapid transit, which means we have a bus which has a dedicated lane, a couple of other things such as off-board fare collection and so on, and which is supposed to be a relatively low resource but high impact solution. And we implemented that on the ring road of Cairo. The second one and the third one are a bit more generic. Both of them are trying to get people to use more public transport, improved walkability by improving walkability around station, meaning, for example, changing the spatial layout, providing safe sidewalks, or an inviting environment. At the same time, we looked at improved intermodality. So we'll have this much more as a topic later, but the idea is generally creating safe places where you can change from one mode to another, mobility hubs, but also information and say the interface in order to know, okay, if I arrive at time X at this station by metro, will there be a bus waiting for me or not? And this is was identified as one of the key barriers of public transportation use currently. So these are the three solutions. And then, unfortunately, I don't have the time to go into the details of the analysis, but I just want to show two examples here. So we look at the score within the simulation. We look at how many people are using public transportation, or what is the mode share of public transportation for trips longer than 1 kilometer, the mode share of walking lower than 1 kilometer, the time spent, and this CO2 emissions created through the trips. And then we compare here scenario 1, which is the auto sprawl, so a sprawl and at the same time increase of cars, against the densification and stable car ownership rate. And just to understand the graphs, that the further it is at the outside, the better it is. So these two are reversed, meaning the longest duration is at the center, the highest emissions are at the center, and the highest score, the highest public transportation and walking share are at the outside. And you see again more or less the same thing as before. The biggest difference is between scenarios, and then you see all the different scenarios here within. So you have the base scenario, and you have a significant improvement across most of the categories from the combined implementation of BRT, the bus rapid transit, walking, and intermodality. But even individual solutions can already have quite a significant impact. So in summary, we tested and replicated the method, and were successful in doing that in a very different context with very different data availability and so on. We found that the spatial layout of the urban form of the city and the car ownerships are two key factors for emissions, for accessibility, and so on. And we also identified that there's a significant positive impact across scenarios, mostly in scenarios which are more probable, but less optimal, let's say, compared to today, such as the autosport one. Mostly there we can see very significant impacts of a combination of relatively low resource interventions. And this brings us to the end. So generally our process is reproducible and open. There are a few data sources sometimes which have to be requested specifically, but otherwise you can find the whole details about the multi-agent based transportation simulation, how the static populations are created, also from our colleague Sebastian Hörl, how the data has been analyzed and the personas has been clustered for the Paris case, as well as how the process has been implemented in Cairo. Some of them are work in progress. So I'm also very happy to have any kind of recommendations and proposals on how that could be different. And then finally, some of the key references where most of our methodology is described. Thank you very much for your attention, and I hope to see you at some other points soon.